Okay, this is the final section of color perception where we talk about color constancy and light constancy. So when we talk about color constancy, there's a question of how do we see the world as having a basic color constancy, because when we're out in different illuminants or we come inside to different illuminants, then those illuminants are emitting different wavelengths of light. What I'm showing there in figure A is that when we are out in the sunlight, that is basically emitting across the electromagnetic spectrum, right? Because that's what's going through the prism or the water to become refracted into the rainbow. That's across the electromagnetic spectrum. If we go inside and we're in these new LED lights, what's mostly being emitted is the shorter wavelength lights. There's some bits of longer wavelengths, but really the majority is these short wavelength lights. And then if we go into lighting where there's incandescent lights, or the tungsten lights, then what they are emitting are those longer wavelengths of light. And so when I have on clothing, or if I look at someone's eyes or hair, all of that is going to be absorbing some wavelengths and reflecting some wavelengths, but that can be shifted around depending on the illuminant. So a green sweater outside under sunlight, though, it appears green, and then when the person comes inside, it still appears green, even though now the reflectance curve has really been shifted or changed. If we look at the reflectance of, let's say, a green shirt, basically, remember, we're not just right at 500 nanometers or 510 nanometers, we are reflecting some of the wavelengths around that in a kind of normalish looking curve, not really, but a little bit. And if we are in the sunlight, okay, that is going to be the basic reflectance curve, because what's hitting me is across the electromagnetic spectrum, and I am reflecting what I am reflecting of that spectrum and absorbing other pieces. But then if I go into the LED lights like we did before, that's going to be shifted down. So if we look at the figure in C, that's shifted down, and that could have could become more blue if that was the way it worked. But instead we have this color constancy where we still see green. If we go into the incandescent lights, or the tungsten filaments, that gets shifted up. That could be that reflectance curve that you're seeing in the orange there in C. That looks more like yellow, but we're going to see green, and green is really different from blue and yellow, and yet we still are going to perceive the green shirt as green, even though it has these different amounts of reflected wavelengths in these different contexts. So it looks like part of the answer to this is what's called chromatic adaptation. So they did a study back in 1989, Uchikawa and colleagues, where the person would be looking at a green paper, and the green paper would be under a basic white light, and then they also had the person's eye under the basic white light. And what you can see from what they're saying there is that the paper still appears green at that point. If what they do instead is they put the green paper under a red light, but the light, the person's eye is still under a white light, then we see a shift of that color to appear more reddish. And so it has been shifted to the longer wavelength lights, or the longer wavelengths. If now we put the person under a red light along with the green paper under the red light, now we see a slight shift, maybe appears a little bit more yellowish, but it doesn't have quite the same shift as we saw in B when the person's eye was under the white light. And so what's happening there is we're having an adaptation to the color of the illuminant, or the wavelengths of the illuminant, and that is compensating and decreasing sensitivity to particular wavelengths. So that gives us partial color constancy. That's part of the answer, but you can see that even in C there, that there is some shift towards more yellowish. And again, that's not what's happening when we walk from outside to inside, and we're seeing people, their clothes don't change color or shift color. So that's just part of the answer. And there are some additional explanations. This is actually a pretty complicated thing that we do. One is that the surrounding environment is really important. I have a question mark there, and I used to ask more questions here, but I've kind of lost my questions. Plus, there's no one to talk to except this screen, so it's not as fun. But we can ask ourselves that, so when we are, part of what's happening is, according to Retinack's theory, is that the cortex is really comparing the different information that's coming from different parts of the retina, and it's more comparative. So the surrounding environment is really important, and you can see these blocks, the blue, yellow, and red, and then the light blue over in the left. And if we see those under different illuminants, that they can, to some extent, change slightly, but to some extent too, we're getting information about what color that is based on the other colors in its environment. And this is even without, these are even objects that are meaningless to us, where we wouldn't know the color. So I'm also going to talk about memory for color just a bit as we go back to, if you remember that study where people recognized the yellow bananas faster than they recognized the purple bananas. So there's also this aspect of memory for color that is influencing our color vision. And there was a similar study to that as people looked at, and I'm going to use bananas again because I can't remember what fruits and vegetables they used, but so if they give gray bananas on a gray background, people still perceive them as being slightly yellow. So our memory for color really is influencing our perception of objects. And if we put all of that together, that results in a kind of color constancy. It really takes the chromatic adaptation, the comparisons with the surrounding environment and what's on the retina, and then also memory for color for us to get this nice, rich sense of color constancy where things just aren't changing depending on the illuminant. We're doing something relatively similar for lightness constancy. We're doing a comparison of what's on the retina. So achromatic colors appear relatively constant under different illuminations as well. And I'm going to show you in these pictures of why that's pretty amazing. If we look at a light, and let's say it's emitting 100 units of light, and with the white squares on my checkerboard, that is reflecting 90%. And with the black squares, it is reflecting 9%. So with the white squares, I'm getting 90 units of light being emitted into my eye. And then with the black squares, I'm getting 9 units. Okay, so with the different shades of gray, I'm going to move between those, right? Well, move that checkerboard out to the sun where you have 10,000 units of light being shown down on it. And now I'm still, the white is reflecting 90% and the black is reflecting 9%. And so now the white is at 9,000 units and the black is at 900 units. And again, we're going to see the white and black checkerboard. But if you look at the black squares in B under the sunlight compared to the white squares in A under the dim indoor light, I'm actually reflecting more light by the black squares in B than by the white squares in A. So the fact that that remains constant, you might be pretty awed and amazed. It's amazing. But it looks like what we're doing is using this ratio principle where, again, we're comparing what's on the retina in the cortex. And so we're looking at the ratios of what's being reflected by the white versus the black versus the shades of gray. In lightness perception, we have this constancy even under uneven illumination. So again, sometimes I have this, I kind of want students to go, wow, that's incredible, like all the time. But our perceptual system is amazing. And these kind of perceptual constancies are really important for our world, seeming to remain the same, even though we're going in and out of really different contexts. But in this example, we're going to look at A versus C. Okay, so A versus C is a difference in the reflectance edge, where those two, A is obviously, right, part of a lighter gray rectangle on this wall, and then C is part of the darker gray part of the wall. So that's a reflectance edge. And if we also look at A versus B now, and B, we can tell, right, that that's a shadow, and that A and B are the same reflectance, and that between A and B is an illumination edge. So that A appears lighter than B, but we know, right, that that's all the same light gray rectangle. And if you compare, so A to B to C, or really B to C, B is darker than C, but we're still able to see it as lighter than C because we can tell the difference between the reflectance edge and the illumination edge. And how we do that, I'm also going to say it's pretty amazing. We're using some top-down processing there, but it's still pretty impressive, and especially this example where we're just aware that a shadow is probably there, and that's how we're perceiving that, is just the awareness that it's probably there. There might be a light little bit of a penumbra that I'm going to talk about here in a second, but a lot of that is just knowledge of the world. We do use different sources of information for figuring out where shadows are, and so meaningfulness of objects, the objects causing the shadow, that can help us a great deal. Again, looks like top-down processing, because I usually ask the question at the end here, but again, you're not here, so I'm just going to start giving a lot of spoilers where we can tell that that's the shadow of a tree, and that those bricks that are in the shadow of the tree are not just darker bricks or dark bricks that are created to be dark in that particular color, right? We know that those are the same color bricks as the ones in the light, and that they are falling in shadow, and the tree helps us see that very clearly, the shape of the tree. Another source of information is the penumbra. The penumbra of the shadow signals an illumination edge, and so if we look at A, that penumbra is, you can kind of see there's a darkness where the shadow of the cup is falling, and then this little bit of lightness in the circle around that before we get into the lightness where the shadow of the cup is definitely not falling. And that little bit of slight lightness is called the penumbra, and it's telling us there's a shadow here. So if you go back to that picture with the wall and the edge of the shadow, there's maybe a very slight penumbra in that picture, but it is helping us. And if you go and dark out that penumbra, things appear slightly different. And so in this, he actually does that for us. He suggests we do the demo, but he does that for us in a picture. And if you see, if we just completely black out that penumbra, that little light area between the darker shadow and the light where there's no shadow, it looks a little bit more like the cup is just sitting on this dark circle with a black edge around it. And you can make yourself see that a lot more easily than if I told you the cup's sitting on a dark circle in A, you'd say, no, that's definitely a shadow and I cannot interpret it differently. And B, it's a little bit of work to interpret it as a shadow and to go back and forth. It looks like the cup's on a dark circle. So the penumbra is another source of information. And this is usually the picture I get to and ask, how do we use top-down processing to interpret shadow? You can pause it and think about it, and different students answer differently here, and sometimes people have specific examples of the sun probably coming over illuminating from above and from the left, and that those look like potentially large bushes or trees. We can also see that the grass is a particular color, and that's probably not changing in those lines, and we have a lot of assumptions about, based on experience, that grass is staying the same. So all of that's top down. A lot of what we understand of lighting constancy really is top-down processing and experience. We have the penumbra. The penumbra would be very bottom-up, but we use a lot of top-down processing to interpret shadows and to maintain some sense of color constancy, even in changing illuminance with different shadows and so forth. So we're going to come back to our questions. We're going to talk about color perception really briefly again as a psychological phenomenon, that this is what's out in the world is wavelength information, and our nervous system and the way our cones and the placement of those cones on that spectrum and the communication between the photoreceptors in the brain and the subcortical structures and the cortical structures, that all of that is helping us to understand this color information. And so there can be individualistic kinds of differences in our interpretation of what we assume the illuminant is. That is one of the suggestions of what was going on with that blue and white versus black and gold, if I'm remembering correctly, that dress that people were perceiving as different. It really is a psychological phenomenon, and it is kind of impressive that we can do this. If we go back to asking our questions of what does color vision do for us, or color perception do for us, again, I suggest you pause this and think through your own answers. And usually this is time for students to discuss, and I don't answer any of these, but there's nobody here except my dog and my cat, and they're not going to answer these questions. So what does it do for us? It really helps us to identify a lot in our environment. For me, being horribly myopic, it tells me a lot of information about my environment, because that's the information that I am receiving, and especially those contrasting colors. People often talk about the feeling of warmth or cold, or attraction to someone or withdrawal from someone, as different situations of red apparently influence us. Different color walls can influence us. And all of that is kind of a deeper, even more individualistic response to colors. It also just gives us beauty, and I think it is something to appreciate. If we ask what physical attributes of the object influence its perceived color, I'm really hoping that it's going through your head that the wavelengths, that for many objects, the wavelengths that are being absorbed versus the wavelengths that are being reflected, that what's being reflected, it's those wavelengths that are giving us our perceived color. Except in the case of those clear plastics, glass, and liquids, where it is really the way the wavelengths are being or passing through those objects. If we ask what physical attributes of an object's environment influence its perceived color, that's what we really did at the end there, right? Where we talked about color constancy and lightness constancy, and how much the environment is going to influence my interpretation of colors. There is a really neat brain games, if you ever watch that. I think it's called Watch This or Pay Attention to This or something like that. And they play some games with different colors. But if we go back to that Joseph Albers, that too, that orange box versus the brown box, those are the same wavelength in different environments, and they do influence how we are interpreting that wavelength information. So context is really important for perceiving color. And then how can we describe color experience? And that I'm going to leave up to you. I've described my experience several times, and usually I don't do it at all. I let you guys do it. So maybe talk to a friend, see what you want to say about your experience and what you get out of color and some of the ways that it's affected you. And that's it. Let's see. For my one class, it's Wednesday, and on Monday we're going to do a tiny bit of perceptual development, and I will have a review out. So ask questions. If you have questions, look at the review at least briefly and say, do I understand what I think she's going to ask about, or what she's thinking when she says blah? Like, what is that concept? Have I never heard this concept? And ask. And my honors class is in a different situation since tomorrow is our last class together, which I kind of am just realizing, or I realized it yesterday, but it kind of freaked me out. So we'll have to do something online. We'll have to figure something out to let you ask questions, and I'll get that review out today as well. I'll get the honors class out today. The other class I'll get out as soon as I can. Everything's very busy. I hope everyone's doing well. It feels weird because for one of my classes, this really is my last class, and it feels weird. I'm saying this again to a screen. I do not like talking to a screen. I do not like not saying my last pieces to my classes in person and saying goodbye. You guys mean a lot to me, and I always miss my classes, and as a class, is who you are and what we were learning, and the questions and the comments and the play off of each other and everything. And this was just a wonky semester, and I hope everyone's doing well with it as we're coming to an end. And you all take care, and I'll talk to you soon.